You should not overcount the sieve. Enumerating the elements of intersecting sets. In a high school class, there are 14 students who play soccer, and there are 17 students who play basketball. How many students play at least one of these two sports? The above question may sound extremely simple. However, we cannot answer it from the given information. Simply adding the two given numbers could yield an incorrect answer. Indeed, there may be students who play both sports. If we simply added the number of basketball players and the number of soccer players, as we would count these students twice. To correct that, we would have to subtract their number once so that they are counted only once, but we can only do that if we know their number. Example 7.1. There are 14 students in a high school class who play soccer, and there are 17 students who play basketball. 4 students play both games. How many students play at least one of the two games? Solution. By the above argument, the number of students playing at least one of these two games is 14 plus 17 minus 4, which is equals to 27. The situation becomes more complicated but still controllable if the students are playing up to 3 different games. This is the content of our next example. Example 7.2. In a high school class, there are 14 students who play soccer, 17 students who play basketball, and 18 students who play hockey. 4 students play both soccer and basketball, 3 play both soccer and hockey, and 5 play both basketball and hockey. There is 1 student who plays all 3 games. How many students play at least one of these games? Solution. We can start our answer as before, adding the numbers of students playing soccer, basketball, and hockey. 14 plus 17 plus 18 results in an overcount because we count students who play 2 of these games twice. Therefore, we have to correct this mistake and subtract the number of these students so that they are only counted once. This yields the number 14 plus 17 plus 18 minus 4 minus 3 minus 5. This is not a complete answer, however. The only student who plays all 3 games was counted 3 times, once for each game, but then she was subtracted 3 times, once for each pair of games. So right now she is not counted at all. Therefore, we have to correct this mistake by counting her. That is by adding 1 to our final answer. Thus, there are 14 plus 17 plus 18 minus 4 minus 3 minus 5 plus 1, which is equal to 38 students in the class that play at least one of these 3 games. We can again represent this situation by a diagram. This diagram is shown in figure 7.2. The reader can probably see that as the number of games increases, the same question requires a more and more tedious answer. Therefore, a general theorem is certainly useful to handle situations of this kind. Theorem 7.3. Sieve Formula. Let A1, A2, A3 until AN be subsets of the same finite set A. Then the size of A1 union A2 union A3 and so on union AN, which is equals to the doubling summation, with the outside summation summing for the terms minus 1 to the j minus 1, with j starting from 1 to n, with the inner summation summing for the size of AI1 intersect AI2 intersect AI3 and so on intersect AIJ, with summation summing for all I1, I2, I3 until IJ, where I1, I2, I3 until IJ ranges all J element subsets of M braces. Before proving this quintessential theorem, we would like to stress that the seemingly complicated expression on the right-hand side refers, in fact, to a conceptually simple sum, the alternating sum of the sizes of all j-fold intersections. The alternating sign is explained by the fact that we have to correct the overcount. The two examples discussed before the theorem were the special cases when n is equals to 2 and n is equals to 3. In the first example, the sum on the right-hand side was a1, the size of a1 plus the size of a2 minus the size of a1 intersect a2. In the second example, the sum on the right-hand side was the size of a1 plus the size of a2 plus the size of a3 minus the size of a1 intersect a2 minus the size of a1 intersect a3 minus the size of a2 intersect a3 plus the size of a1 intersect a2 intersect a3. Proof of theorem 7.3. Notice that an element not in A1 union A2 union A3 and so on union AN is not counted in any term on the right-hand side of 7.1. Thus, we only have to show that each element of A1 union A2 union A3 and so on union AN is counted exactly once on the right-hand side. To do that, pick any element x in A1 union A2 union A3 and so on union AN. Let S, which is subset equals to n braces be the set of indices so that x in AI if and only if I is in S, and let little s be the size of S. Note that little s is greater than or equals to 1. As x in AI only if I is in S. A t-fold intersection. AI1 intersect AI2 intersect AI3 and so on intersect AIT cannot contain x unless I1, I2, I3 until IT is a subset or equals to S. So when determining the number of times x is counted by the right-hand side, we only have to consider the intersections involving the AI which are indexed by S. On the other hand, each of these intersections does contain x. Therefore, the right-hand side counts x once for each of these subsets with alternating signs. So, altogether, the right-hand side counts the element x, little s minus little s choose 2 plus little s choose 3 minus little s choose 4 and so on plus minus 1 to the s minus 1 times s choose s, which is equals to 1, times. To see that the left-hand side of 7.2 is indeed 1, subtract 1 from both sides, then multiply both sides by minus 1 to get 1 minus s plus s choose 2 minus s choose 3 and so on plus minus 1 to the s times s choose s, which is equals to 0, which is equals to 1 minus 1 to the s, which is true by the binomial theorem and is further explained in theorem 16.21.